Alright, the argand diagram and complex geometry. So in the previous video we went through how to solve complex algebra in the form of, say, z to the power of 5 minus 1. In that previous video I think we found the sixth roots of z equals -8. The sixth roots of this equation. So that's what we did in the previous video. So let's begin this video by just kind of going through that again on this new problem and just recalling all of those skills that we learned. So if we were to solve this problem, z to the 5 minus 1 equals 0. We want to solve that in the complex plane. So remember that in that previous video, we decided that if we let z equal r times cosine theta plus I sine theta, so polar form, then z has n distinct roots of this form. Okay, so we take the nth root of r, cosine of the angle of our first root, plus 2 pi k over n, plus I sine theta plus 2 pi k over n. And we just count up where k goes from. Little k went from 0, 1, 2, up to n minus 1. So that's what we did on this problem here. We solved the solution for this, got W0 through to W5, and we plotted them on the argand diagram. We went through and we found that they all lie on a circle and they are equally spaced. So what that meant was that each of these roots, when connected, made a regular n-sided shape. So for this one, it made a regular hexagon. For this one here, we're expecting a regular pentagon. So, and that's really important, that regularity of these shapes. So, we're wanting to solve, just like this question, z to the 5 equals 1. Or, cram this in a little bit, but we want the fifth roots of z to the 1. So in polar form, we let z equal cosine of 0, because on the argand plane, or on the argand diagram, 1 is here. So the argument of this is obviously 0. And you can see how in your trig identities that's going to come about. So cosine of 0 plus I sine of 0. Sine of 0 is 0, but cosine of 0 is 1. So that's true in polar form. So that's our W0. So W0 is 1, or cosine 0 plus I sine 0. So now let's get all the other roots. So W1 would be cosine 0 plus 2 pi over 5, so 2 pi over 5, plus I sine 2 pi over 5. Now the argument for a complex number has to be the same in the real part and the imaginary part. Otherwise you couldn't write it as cis theta, right, in that shorthand form. Also, if these arguments were different, it's not geometrically speaking, but in my mind, I think that that's kind of like twisting your imaginary number, because you're going to some different argument for the reals than for the imaginaries. So now we're just going up in 2 pi and simplifying if it's even necessary. So 4 pi over 5, 6 pi over 5, 8 pi over 5, and obviously there's no fifth because that's just going to be 10 pi over 5, which is 2 pi, and that's the same as going all the way around back to 0. So then they start to repeat, don't they? So that's a bit of a recall. And then we plotted, I can plot these complex numbers on the argand diagram. So hopefully you can see that. We've got 1, and then this is cosine 2 pi over 5, I sine 2 pi over 5. Then we've got cosine 4 pi over 5 plus I sine 4 pi over 5. And so on and so forth until we get our fifth roots and we have a regular pentagon. Cool. So what we want to do is we want to now go from the regular shape on the complex plane, or an argand diagram, and we want to go back and write the equation. Okay, so what does that mean? Let's have a look at this example here. We want to write the polynomial of, we want to write the complex polynomial for this problem here. So how many sides does it have? Okay, it's 7 sides, so we have a regular heptagon. So there's 7 equally spaced roots, and they're all going to lie on a circle. So what is the radius of this circle? It's very tempting to go 2 and a bit and go here, but actually here is our first root. So W0 is actually negative 3i. Okay, so that means that z to the 7, so our complex number raised to the power of 7, is equal to this number here raised to the power of 7. Okay, well that's not very tidy, so we're going to tidy this up. So my working is a wee bit long and complicated here, but this is basically, you've got negative 3 to the 7, I to the 7. What is I to the 7? What? I to the 0 is 1, I to the 1 is I squared is negative 1, I cubed is then just negative I4 is just going to be 1, I5, and you can see that now we're now repeating I6 is the same as 2, so negative 1, and I7 would be the same as 3, so negative I. So this is just going to be negative 3 raised to the power of 7 times negative I. And this comes out to being 3 to the 7 times I. Okay, so this is our regular heptagon. This is our equation. Z to the 7 is equal to 3 to the 7 I, or if we wanted this to equal 0, Z to the 7 minus 3 to the 7 I equals 0. Or if we expanded this out, Z to the 7 minus 2187i equals 0. We've now found, just by using one of these solutions, we've found the equation that gives these roots of this regular heptagon. So that brings in a little bit of a note. So generally, if we can find any one root or a vertex of a regular n-sided polygon that's centered at the origin, say it's W, because that's what we've been using, so W0 the first one, then the equation of the polygon will always be Z to the n equals W to the n. And that's what we've done here. And as you saw, if we were to write the equation of this polygon, well, this is a 5-sided shape, so it's a pentagon. So that means that Z to the 5 is equal to 1 to the 5. Or Z to the 5 equals 1. Or Z to the 5 minus 1 is 0. That would be the quick and easy way of writing that equation. Hopefully that makes sense. I'll put this back in because we've got a wee bit more to go. So side note, if the polygon has a center other than the origin, then recall that the translation by replacing z with z minus a plus bi to shift it to the center, or to, if you find the solutions, then shifting all those solutions back. Okay. That's a wee bit of information for us, but let's just do another example. Okay, Question, the third example is this one here. What do you notice about that straight away? It's non-regular, which means that these points don't all satisfy the same equation. You might want to pause the video and see if you can find the solutions to this problem. Okay, I'll get my ruler out and green pen. Notice that this is actually the composition of two shapes. It's a bit easier to see when you've actually got a printed out diagram, but I've done my best to draw this. We can connect these points and these points. So what you can hopefully see there is we have a square, which means a square is a four-sided shape. Z to the 4 is equal to that first root. It could be either of these, to be honest. It could be any. Actually, we might show that that would be the same. Would be z to the 4 equals 4 to the 4, or z to the 4 equals, I believe, 256. So one solution, z to the 4 minus 256 equals 0. That equation there is going to give you this one, this one, this one, and this one. Now, if we went negative 4 to the 4, even power would give you 256. If we started with 4i, well, 4 to the 4 is 256. And I to the 4, as you saw on that previous bit of paper, would take you all the way back to 1. And it's very similar for the negative 4 to the I. So it actually doesn't matter which one we start with, as long as we start with a vertex. So there's 4 of our solutions. Okay. What we now need is we need to find these two solutions. So I'll use blue pen here. Run out of colours. But if we connect these up, and this comes with a bit of experience, but you should be able to see that this is a regular, or it should be a regular triangle. So that means that z to the 3, I'll do it up here, so it's matching the same format we've done. Z to the 3 is equal to 4 to the 3. Or, going all the way down, z to the 3 minus 64 equals 0. Okay, so we've got two equations that equal 0. So obviously multiplying these are going to equal 0, and this becomes z to the 4 minus 256 multiplied by z cubed minus 64 equals 0. So there's our polynomial that gives those solutions. Even though it appeared to be non-regular, we have now found the equation of the polynomial that gives those roots, where z is the complex number x plus iy. If we want this in another form, we could write this as z to the 7 minus 64 z to the 4 minus 256 z cubed plus 16,384, and that's equal to 0. Just in case you had to do a comparison with some other polynomial and compare coefficients, that's the expansion of it. Yeah, I just looked at that, and that's obviously the expansion. Pretty easy. All right, we have another one that we can go through, and that'll conclude the video. This one here. I'll bring this down so it's in the frame. All right, how many sides does this shape have? Or how many vertices, sorry. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have an 8-sided shape. Sorry. 1, 2, 3, 4, 5, 6. Yep, so 8-sided shape, but it's again non-regular. So we need to think of how we might be able to solve this problem. So we could make it into two squares by joining every second vertex, and having two overlapping squares, but I want to show you a slightly different way of doing this problem. So what I might do is I'm going to create this square in here, and this is going to form points, 4 more points on the circle. So this is all obviously by hand, so it's not perfect, but hopefully it'll be enough to illustrate my point. Okay, so that's meant to be a square, so just imagine that that's a square. So now what should happen is that all of these points now should form a big circle. Okay, again, I'm lacking the ability to print out perfect diagrams and put them in the video, but hopefully we'll manage. So what we want to do is we want to get all of these points, which are obviously, how many are there? There's 12 now, 12 points, so z to the 12. Mine are equals, we'll just go with the same form as 4, equals 2 to the 12. So it's the 12th roots of that equation. So if we were to rearrange this, that's z to the 12 minus 4096 equals 0. But that's given us 4 solutions that weren't originally in the diagram. So we have to somehow remove these 4 solutions, which are z to the 4 equals 2 to the 4, or z to the 4 minus 16 equals 0. We have to remove these solutions somehow. Well, you can't divide by 0, so if we remove them, we could write this whole problem out like this. There we have it. We would then, I should have done a second diagram to bring it back in clean, but we would have our original shape with just those points, because it would be z to the 12 minus 4096 to give us all of the solutions. But you can't divide by 0, so the 4 points that satisfy this equation wouldn't be drawn. So that would be, this one wouldn't get drawn, this one wouldn't get drawn, this one wouldn't get drawn, and that one wouldn't get drawn. And it would leave you that irregular polygon. So hopefully that makes sense.